Okay, recording on. I'll get started here. As I was just saying, you're getting near the end of the course and you're learning like some of the more abstract concepts now, I would say. This is review session 11, only one left. Wow. And this is today is 4/17/25. Um, the stuff at this point in the class kind of all overlaps. It's just frequency domain stuff, but I guess what you've done this week more of, as it seems, doesn't really seem like it's particularly different from last week per se, but just like more transfer functions and like uh Bodie plots and stuff like that. The good thing here is that I don't think he puts Bodhi plots on quizzes, so I don't really know. Like, I think this week's quiz will just be like last week's quiz, but with different questions. I really have no idea what will be on this quiz. It'll be something related to transfer functions and maybe like resonant frequency, and maybe he could do a Bodhi plot on the quiz for the first time ever. I don't know. Make sure, I mean, like, yeah, the advice as always is just look at what was on the homework and make sure you like understand it, I guess. Other than that, yeah, I will do, I'll start with like last week's quiz, that one question from it, or the harder question from it. There was the average power, oopsies, there was the average power question, and then there is the, yeah, okay, there's the average power question, and then there was the actual like transfer function question that was more complicated. I will just do the transfer function question. So we have V out and V in, and this is L, C, and R. And the question was find H of omega, the magnitude of H of omega, and omega naught, which, if you remember, is the frequency such that the imaginary part of the input impedance equals 0, which I will explain once I get there. So first off, what is H of omega? So H of omega is basically just, so H of omega, as you all hopefully know by now, equals V out over V in. The other way to think about this is that V out equals H of omega times V in. So if you can write V out in terms of V in and then like divide it, then what you're left with is H of omega. So what we'll do here is just find V out. So V out, if you think about it, V out is just the voltage at this point. So I just do a voltage divider. So V out equals, and just to fill this in, this is actually J omega L, and this is uh, 1 over J omega C, right? So what we have here is that V out is R over R plus J omega L plus 1 over J omega C times V in, right? So then from that, you can instantly get that H of omega equals V out over V in by just, dividing it over. And then what you're left with is R over R plus J omega L plus 1 over J omega C. Now, in this class, whenever you're doing a transfer function, in order to like do any of the actual useful stuff with the transfer function, you want to get all of the imaginary stuff out of the denominator. So we want to do that. So if we do some algebra, right, we can notice that this is, okay, this is R plus J times omega L plus 1 over omega C, or minus 1 over omega C. There's like some algebra on that, but just trust me. And then we multiply this by R minus J omega L minus 1 over omega C over R minus J times omega L over minus omega C, right? And then this is like enough. So then your final answer here would be like r squared minus j r omega L minus 1 over omega C over r squared plus omega L minus 1 over omega C squared. And this would be your h of omega. And this is our final answer because we have a very clear real and imaginary part, right? And the denominator is all real. So this is in effect like the a plus bi form. And that's what we want in this question. A plus jb form. Because it says, oh yeah, it says in the question it said in standard complex number form. So yeah, in the question it'll say what form it wants it in. So here in standard complex number form, which is different from standard form. Because standard form is the thing you've been learning in class. This is just standard complex number form, which is just a plus jb, you know? So we have that. And then it asks for, okay, what is the magnitude of the transfer function, which you can write as like it's written in the answer key as mr of omega, which I don't really get. I would write it as the magnitude because that is what it is. The magnitude of h of omega, which is very simply, right, the real component squared plus the imaginary component squared. This is why we have you write it in that a plus jb form, because then this is very straightforward to find. So it's the square root of the real component. So the real component, right, is going to be this, right? So r over all that stuff. And the imaginary component is this. Hopefully that's pretty clear. So then we get, and keep in mind, it's all that squared, right? So we have r squared over r squared plus omega L minus 1 over omega C squared plus, and we can basically drop the minus because it's getting squared. And when it says the imaginary part, we don't care about the j. So this is very simply just like r omega L minus 1 over omega C over r squared plus omega L minus 1 over omega C squared. It's a big expression, but it's pretty straightforward how I got to it, right? Um, and then this is like almost enough, but they said to simplify it a bit more. So you can simplify this a bit more. You can square the top parts and combine the denominators, right? So we have, because they both have the same denominator, right? It's r squared plus omega L minus 1 over omega C squared. And then on the top, we have r to the fourth plus, what is this? It's like r squared omega L minus 1 over omega C squared, I believe. Oh, I'm getting a phone call. Hold up a sec. Let me go see what my roommate needs. I'll be back in a second. Okay, sorry about that. My roommate is sick and needed something. Um, anyway, where were we? We were here. I what was I doing here? What was I at? Give me a second to sorry, find my bearings again. I think there's a slight error in this answer key actually. Okay, anyway. We're here, right? That's squared, and then you can just like unsquare this denominator here, and that would be your like final. Or you can factor out an r from the top as well, so you can get like r times the square root of r squared plus omega L minus 1 over omega c squared. And on the bottom, you can unsquare that and like r squared plus omega L minus 1 over omega c squared. And that would be your magnitude of h of omega. Okay. Now for like the final part, which a lot of people like got the right answer by doing it the wrong way, which is like, okay, I guess. Um, it's asking for the omega naught. And omega naught, as I said, is the W such that um the imaginary component of Z in equals 0, right? So Z in this case is going to be the impedance looking in from like this way. So it's asking like, what is the impedance if I go out of V in and want to come back into V in? So in that case, it's just these three components in series. It's like very, very chill there. So so basically we say, okay, so Zn equals j omega L minus or plus 1 over j omega C plus R, which we can rewrite as R plus J times omega L minus 1 over omega C. And then, okay, we want the omega such that the imaginary part is equal to 0. So then we say 0 equals omega L minus 1 over omega C and solve for omega, which, I mean, we could like put this here now. So it's 1 over omega naught C equals omega naught L multiply let's see. Yeah, you multiply stuff together. I don't know. Yeah. Yeah, divide over the L, multiply the omega, and you get omega naught squared equals 1 over LC. And so finally, your omega naught equals the square root of 1 over LC. Very cool. And I think you've like seen this before when you were doing some other stuff in the class. So that's how you do that question on the quiz. Um, yeah, I'll do like another question like that, I guess. Um, let's see. Magnitude of the. Okay, this question seems like interesting, I guess. Yeah, sure. Could see him signing something like this. I don't know. We got our VS, um, what we're going to call the source inductance and the source resistance. And then that goes into an op amp with the minus on top, positive on bottom, and then like so. Yep, we got a V out, we got a L, F, and a R, F. And it's saying get a simplified expression for the magnitude in dB in standard form. So, before we do anything, we remember that we are doing an op amp. So this is 0 volts, this is 0 volts. That makes our lives easy, right? And this is going to be J omega LS, and this is RS, and this is going to be J omega LF, right? Um, then moving on, we write our node equation just like at Vn, right? We got uh yeah. Or no, actually okay, you can actually yeah, before we do that, it is a bit better to combine these two and these two, right? So we can say like ZS is going to be like the equivalent impedance of these two components together, right? So that would very simply just be RS plus J omega LS, right? And likewise, ZF is going to be J omega LF in parallel with RF, which would be equal to J omega LF times RF over like RF plus J omega LF. And then what are they doing here? Yeah. And if you want to make it look more like standard form, I guess, you can make this J omega LF over 1 plus J omega LF over RF. Not exactly sure why you do that immediately, but I'm sure it will become apparent later. So then at the end, we do a node. So this is just same kind of node you've done before. We got 0 minus Vs over what is now Zs, right? I'll leave them, the reason it's nice to do this is then you can just leave it in variable form, right? And then plus 0 minus V out over Zf, right? Equals 0. And then if we solve for V out, dot, 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 we're just going to get V out. This is just like a normal inverting amplifier. Um, so it's going to be negative ZF over ZS times VS or VN. On to the question, I was a little bit confused about this week. Are we trying to convert the formula into a different form in terms of dB? So this is saying, this question is like, I'm not exactly sure like what it will be on the quiz again. But when it asks for like a magnitude question, it's saying, okay, first find h of omega, then turn it into the magnitude of h of omega, which you can also write as like the magnitude, and then turn that into decibel form. So it's like all the same thing, just like thinking about it in different ways. So those are like the steps though. Anyway, um, moving on here. So the first thing we have to find though is that h of omega. So h of omega, I'll draw a little arrow here. H of omega equals V out over V in. So that would be VO over VS, which is just going to equal negative ZF over ZS, which we found both of those. So with those, we have minus ZF is J omega LF over 1 plus J omega LF over LR. And then all of that over, how'd they do that? Oh, okay. Oh, I see why they did it like that. Okay. So up here again, you can rewrite this as like, because remember for standard form, you want all the real components to be 1. So you can rewrite it like this, and then it like looks the same on the top and bottom, and it's nice. Uh, so it's this times like R, oh boy, hold up a sec, RS. Yeah. So L, what am I writing here? Okay, RS. Yes, no, RF. Okay. That, yes, okay. So we have this, and then we want to make sure this is in standard form. So what we have to do then is just make it so that you have like one numerator and one denominator. So this part here, remember your like division rules, this can just go to the denominator. Uh, so this is going to be Give me a sec. Why did they just get rid of the minus sign? What? I'll leave the minus sign in yet. But you're getting the magnitude, so eventually the minus sign will go away anyway. Uh, but what we get is j omega LF. Um, actually, what are they? Oh, okay, okay. Yeah, okay, I see. So this is all algebraic manipulation to make it in like a nice standard form. So I will so we have if we move like this constant and this constant out, right, we get LF over RS and then times J omega over 1 plus J omega LS over RS times 1 plus J omega LF over RF, right? And this is looking a lot like the standard form you learned in class, right? So then what we have here is we can rewrite this. So you can either write it like this, or you could have written it like that, right? Those are both identical. So then you can write this for standard form, it would be like j omega time over omega 1, and then 1 plus j omega over omega 2, and then 1 plus j omega over omega 3, where, omega 1 equals, and now these are all going to flip because they were coefficients before, but now they are um not coefficients. Now they're the other thing. Hold up, I wrote this backwards. Now they are now they're on the bottom of the fraction. So you gotta flip them. So RS over LS and omega 3 equals RF over LF. Very cool. So this is the standard form though. And then the reason we like standard form is because the question told us to like it first. But then also because it's like very easy to turn this into the decibel form, right? So if you remember something in decibels, uh, so if we take the magnitude of this, then would just like for all intents and purposes, it would get rid of the minus sign. I'll like actually just write this out how they say to do it here because it's pretty straightforward. So the m of omega in decibels is going to be equal to 20 times the log of h of omega, right? That's like the definition of decibels. So then we use our log rules to like split this expression into all of those. So it would be 20 times the log of j omega over omega 1. And it's to be specific, it would be like the magnitude of j omega over omega 1 minus 20 times the log of the magnitude of 1 plus j omega over omega 2 plus, or actually yeah, minus running out of space here, minus 20 times the log of kind of the same thing, the magnitude of 1 plus j omega over omega 3. And then if we can take the magnitude of these things, that's like something that we can do quite easily, right? So that is going to be like, there's like two more steps kind of. So the magnitude of something that's purely imaginary is just like the value itself, right? And then here it's minus 20 times the log of the square root of 1 squared plus omega squared over omega 2, or it's like that, right? It's the real part times the imaginary part, or the square root of the real part squared plus the imaginary part squared. And then minus 20 times the log of, again, the real part squared plus the imaginary part squared. And then you can use your log rules to like get rid of this is equal to the power of 0.5. So you can move this to the front. Your logarithm rules, you know this. And your final thing for like the final answer, the magnitude in decibels is equal to 20 times the log of omega over omega 1 minus 10 times the log of 1 plus omega over omega 2 squared minus 10 times the log of 1 plus omega over omega 3 squared. And this would be your final answer. So it's like a long process, but none of it is too complicated, right? Yeah. And now I will find more questions to do. Yes, sec. Oh, um, okay, sure, I'll do this. So in this question, you are given a transfer function, and you are told to find the corner frequency for it. Two, you are told to get the magnitude in decibels. And three, estimate uh the magnitude the estimate this. So I could have just written it faster than copying and pasting it, I think. But estimate this as omega goes to infinity. Mhm. Um, oh, okay, good question on the last one. So here you're asking about why we just delete J for this. Because remember this these bars, it's asking for the magnitude of the transfer function. So we like take the three terms because it's like log of like a divided by b is equal to log a minus log b, right? So if we're asking for log of the magnitude of a minus the magnitude of b, it's like that, right? But then the magnitude of like a complex number, so like a plus jb is equal. Oh, I wrote that. A plus jb is equal to the square root of a squared plus b squared, right? So it's the real part and the imaginary part. For these, we did that. This is the real part, and this, excluding the j, is the imaginary part. For this one, however, it's like 0 plus j omega over omega 1. So if we took the absolute value of this, it would be 0 squared plus omega over omega 1 squared, and then this is just omega over omega 1. So yeah, that's why. It's just the other way to think about it is like if you were thinking about this on the complex plane where you have the real and the imaginary part, when it's asking for the absolute value, if we had like, 2 and 2j here, then the magnitude of that is like the length of this line. However, if we have a purely imaginary part, right? So if it's like j3, or as in this case, we had like j omega over omega 1, then the length of this line is just omega over omega 1. Yeah. How did I get 10 log for the final answer? That's what I said right here. This is just like a log rule. Log of like x to the log of like x squared is equal to 2 log x, right? So or like log of x to the n is equal to n log x. So in this case, we had a bunch of like 20 times log of the square root of x, and that is equal to 20 times the log of x to the 0.5. So then we just move that 0.5 to the front. So then 20 times 1/2 is that. Yeah. Okay, back to this question. So it's asking us to find the corner frequency. Bruh, I'm getting all the phone calls today. That's this one I probably should answer, but I'll answer this. Fucking hell. Okay, I'll pick this one up right now. Okay, back again. Sorry about this. Everyone's hitting my line today. Um, anyway, corner frequency. We need to find for the corner frequency, we just need to put it into standard form and then see what's in the denominator, basically. So we want to turn this into standard form. So to start by doing that, you like make all the real parts one. So we're dividing by like 2r squared. So this is then equal to, if we divide everything by 2r squared, 1 plus j omega, and I'll like write it up here. So it's j omega 3lr over 2r squared, right? And on the top, we're going to do the same thing. So it's lr over uh, 2r squared. And then, yeah. And then if we do a little bit more simplification, right? Simplification. You get, am I overthinking this? No. Yeah. You get like j omega over, um, this r cancels, that cancels. So you'd have like 2r over L. And then on the bottom, you had 1 plus j omega over this cancels with this, and you're left with 2r over 3L. You see? Very cool. Um, and I believe the corner frequency for the purposes of, I don't really get. I think you can write both of these. Like this would be like omega 1 and this would be omega 2. But I believe I guess, yeah, actually, the corner frequency per se would be this one. So omega c would be 2r over 3L. Yeah. Um, yeah, when in doubt, like, I don't know, stick with the one that also has the real component is probably better, I suppose. Um, Part two, find the magnitude. So we have it in this nice form now, right? So if we do the same thing we did last time, log or 20 times the log of h of omega is equal to 20 log e. Oh, okay, I guess the way you actually write this is like this would be, this is 3 omega c and this is omega c. Okay, sure. Yeah. Yeah, I guess that kind of makes sense. This part of the class, it's like this is all like notation. If you show that you know what you're doing enough, you'll be fine. How do I know that omega equals 2r over 3L? Because right here, right, we said that we divided by 2r squared. 3lr over 2r squared equals 3 over 2 L over R, right? However, we want it to be in the denominator. So right here, it's being multiplied. So if we want it to be divided, we have to flip it over. So 3L over 2R becomes 2R over 3L. And that's how we get that. How did I know how to divide by 2R squared? Because to find the corner frequency, we want to put it into standard form. And to put it into standard form, we want to make the real part of things be 1. So this is the only real part. So we divide by 2r squared to make it so that we have 1 here. What is the corner frequency? The corner frequency, I feel like this is a bad question, but the corner frequency for like anything is the frequency where it's like h of omega c equals, it's like 1 over root 2, which feels arbitrary, but you like they use it a lot in electrical engineering or like in a lot of things. It's just like it's the point where you like say the function starts going down. So like if you have like an R and a C, this is like the standard example. This is going to have, I think just off the top of my head, it's like 1 over, it's just 1 over RC is the omega C, which means that like the transfer function for this this is like the kind of standard Bodhi plot thing you've seen where it's like this and then it starts going down. So 1/2 is equal to like mine or 1 over root 2 is minus 3 in decibels. So that's like around here or something. So it's like this is the point that is omega c. If this is like 0 dB, then this is like minus 3 dB. And that's what it is for omega c. And generally, like the way you do this is you look at the denominator and figure out when the denominator, like the magnitude of the denominator will equal root 2. So here, right, we want to find out, so we turn this into like the one form, and then basically doing this is like a shortcut to it. So we want to find out when like the magnitude of 1 plus j omega 3L over 2R equals root 2. And what he's been talking about in class is just like how to do that like without having to go through all of this. And what you find is that like omega equals or this shouldn't be here. This is like actually I wrote this badly. It's like that, right? Because you're finding the magnitude. Uh that and then you'll end up getting like 2R over 3L. Because you want to make this equal 1. Because if this is 1, if this is 1 and this is 1, then 1 plus 1 is 2. I know I'm explaining this badly, but frankly, it's like not. I think this question is like bad because there should be like another corner frequency for the top one, but they didn't write it like that. But you see how this is like 3 times this value? Hopefully, yeah. For now, just think about it in terms of what's in the denominator. You want to put it into the 1 plus j omega over something form, and then that something is probably going to be the corner frequency. That is what I'll say for now. And then I will move on with the question. But anyway, what we had here is the part in the numerator is going to be the magnitude of j omega over 3 omega c, and then minus the part in the denominator. So 20 times the log of the magnitude of 1 plus j omega over omega c. Right. So then we get 20 times the log of, oh yeah, you can like, this is like a stupid way of doing it. But it's like, no, it's like fine. Okay. I'll just do it like this. So this is like 20 times the log of omega over omega c or 3 omega c minus 20 log uh or I'll like yeah, 20 log the square root of 1 squared plus omega over omega c squared, right? So this is like, you could simplify it further by putting this over here, but we're not going to do that for now, and you'll see why in a second. So, and this, you can also like further simplify it a bit more. This is like 20 log of 1/3 times or plus 20 log of omega over omega c minus 20 log of, all that stuff. And yeah, so that would be your H or your M of omega in decibels. And then for part 3, it said estimate omega, estimate it as it goes to infinity. So this is like where you gotta like, use your brain a little bit. So as omega goes to infinity, right? What's going to happen to these terms? Well, as it goes to infinity, this term will get really big, and this term will get really big. Let me actually write this back in. So what we have here, right? Or actually, oh, okay, no. So the important part for as it goes to infinity actually is that this one stops mattering, right? Because we have here, right? If omega gets really big, then this term will overpower this term, and this will like basically equal 20 log of the square root of omega over omega c squared, right? Which is just 20 times the log of omega over omega c, right? So then the thing you're supposed to notice in this question is that, okay, we'll end up with 120 log omega over omega c from this term and this one. So we have a positive one and a negative one. So when omega goes to infinity, what we end up getting is that omega or m of omega will just equal that 20 log of 1/3, which is like roughly equal to 9.54 decibels. And that would be that. So omega and omega c are different. Yes, okay. Yes, very much so. Omega c is a number, and omega is the frequency. So the point of the transfer function is saying like, okay, if I omega is like the x-axis there, right? The transfer function often looks like that or something, and it's saying, okay, for let's say this is like the magnitude, right? Magnitude in decibels. What the transfer function says is if I put in some sinusoidal input, so if I put in some sinusoidal input of, or it's like a cosine, for some frequency like omega t, right? If I put in some function as the v in, then what the h of omega tells us is what the like magnitude of it will be for the output. So it'll have the same frequency, but it'll have a different magnitude, and it'll also have a different phase shift. And that's what the transfer function tells us. And omega is like the important part, because what it's saying is that as your frequency changes, you get different behavior. So like with that example of like the resistor and the capacitor, right? The idea here is that at low frequencies, right? So at DC, so when you only have DC, okay, let me answer this question in the chat first. If there are two parentheses in the denominator, will there be two corner frequencies? Yes, there will be. That is correct. There will be. Yeah. When you don't have basically, I think with the corner frequencies, just like only really care about the denominator because the stuff in the numerator is a pole, if you learned about that, which or no, it's a zero, not a pole. Yeah. And you only care about the poles for the corner frequencies. Again, like this is complicated stuff that makes more sense if you take a signals and systems class. They like give an introduction to it in this class, and it's like not the most clear, but try your best. Anyway, back to this, like giving a more intuitive explanation, right? So the idea with this circuit, right? This is like a low pass filter. I talked about this like last review session a bit. But the idea here is that, okay, this is a voltage divider where the resistors, if you think of it as just resistors, it's like you have the resistor R and you have the resistor negative J over omega C, right? What this is saying is, okay, first off, intuitively, you know that when it's just a DC voltage, a capacitor is like an open circuit, right? And you can see that here. So at DC, so when omega equals 0, right, this goes to infinity because it's like something over 0, it's infinity. So that's why like it's so at DC, this is an open circuit, and what you get is 0 dB. 0 dB is equal to 1, right? Because 20 log of 1 will get you 0. Log of 1 equals 0, because 10 to the power of 0 equals 1. Yeah. So 0 dB means that the signal from the input to the output does not change. However, as frequency increases, right, this term will get smaller, or we'll get smaller. Because like if we're at 1,000 hertz or something, so 1,000 hertz would be 1,000 times 2 pi here. This is radial frequency or like angular frequency and not frequency. They're different things. Or actually, this would be, yeah, 1,000 times. this is how many radians it moves in a second. Hertz is like times per second. I always have to think about this when I'm thinking about it. But it's like, yeah, 1 hertz. Yeah. So let's say we're at let's just say the omega is 1,000 for the sake of argument, right? Then this would become negative j over 1,000 times your capacitance, which is a significantly smaller number than infinity, right? So what you see is that if this is a voltage divider, okay, we have one resistor here that's set, and it starts with this one being huge, right? If you have a huge resistor on the bottom, then that one's going to like get all the voltage. So that's why it's like practically 0 dB, because all of the voltage is going across the capacitor. However, as frequency increases, the resistant, like the impedance, or I'm just going to call it the resistance here, the resistance of this will go down. And as the resistance of that goes down, then it's like an actual resistor, it's actual voltage divider, like the voltage is getting divided. So then the voltage here will not be the same as the voltage here. So that's why it like starts going down. And then the corner frequency is just like an arbitrary point. It's not really arbitrary, but it's like the minus 3 dB point. And that's just the point that they think about for like that's where we start saying that the frequencies higher than that are being cut off. That's why it's like the corner, because it's like the corner of this curve. Yeah. And like this is the omega and this is the magnitude of h of omega. And then there's also stuff on like the phase, but I'm not going to talk about that. But yeah, omega c is this, but omega is like a variable, you know, whereas omega c is just a point. Yeah. Um, Surely I can find one more question to do with my time here. I think I did that one last time, so I will not do that one now. Yeah, some of the questions in these quizzes can get like really long because it's all variables and it's like annoying. I already did like most of these last week, I think. You guys are still like a week ahead-ish of the previous years. Okay, I'll just do this. I don't think I did this one. So this question is saying find omega naught. Omega naught is again different from omega c. But then question two is finding the value of the transfer function at omega naught, which is a different thing. So again, the resonant frequency is the omega such that z, the imaginary part of the input impedance is 0. So again, that is saying the input impedance is like the impedance going from one part of Zn back to the other part of Zn. So here, yeah. So here in that case is going to be just these three in series, right? So Zn equals, I'm just gonna leave it in variable form while I'm doing the math, and then we can plug stuff in at the end because it'll honestly make our lives a bit easier. So it's just R plus J omega L plus or minus J over omega C. And then this will equal R plus J omega L minus 1 over omega C. And then we want to find when the imaginary part of this is 0. And I did this exact thing earlier. So you end up getting that omega naught equals the square root of 1 over omega 1 over LC. And then if I plug in L and C, right? Or so it's the square root of 1 over L was 0.1, and then C is 10 times 10 to the negative 6. And that gets us 1,000, and the unit is radians per second for omega naught, right? Cool. And then it's asking us for, okay, what is the magnitude of the transfer function at that value? So we first need to find the transfer function, and then we need to find the magnitude of the transfer function, right? So the transfer function here is going to be just the same like voltage divider thing we've seen before. So remember, you can write V out equals V in times the impedance of the capacitor over the impedance of the resistor plus the impedance of the inductor plus the impedance of the capacitor, right? So then we can say that V out over V in, which is the transfer function, is equal to that negative J over omega C over R plus, and then I'll like combine these just in one step here like I did above, minus J over omega C. And then it's asking us, so basically like if you wanted to put this in standard form or change it however you want, you can. However, we just need to find the magnitude of this at 1,000 hertz, right? Or not 1,000 hertz, 1,000 radians per second. And we have all the numbers, right? So if you really want to, you can just like plug this into your calculator and it can do it for you, like the whole thing, like just all at once. However, like you can literally just like go into your calculator, assuming you have like a TI-84, but you can just like literally put in negative, or in the calculator, it'd be like you can do the absolute value on your calculator, and you can do like negative I over 1,000 times 10 to the negative 6 over 20 plus I times 1,000 times 0.1 minus I over 1,000 times 10 to the negative 6. And this will like get you an answer. However, you can also like simplify it nicely. So if we want to find the magnitude of this, then we get the magnitude of the top over the magnitude of the bottom. Someone asked, what does omega naught mean when imaginary particles? Okay, so the resonant frequency of any circuit is like when the it's when the like inductors and capacitors basically cancel each other out. And what that means is it's when the imaginary part of the input impedance is zero. So like what that actually means is like up for like you got to think about it a bit. But basically what we did here is, I guess I should have added another step here. I'll just like write it in here. So we find the input impedance here, right? And then we find out what its imaginary component is. And then you would set the imaginary component equal to 0. And then that is your omega naught. Yeah. Anyway, for this part, like, okay, so you can plug this into your calculator and you will get a number. And I think it's like 5. And it would be, yeah. However, you can also, do a little bit of math to simplify it if you don't have a good calculator like that. So this would be 1 over omega c just on the top, and then on the bottom you'd have the square root of r squared plus omega L minus 1 over omega c squared, which is, not the nicest thing to look at. However, oh boy, you can like do quite a bit here. Um, Actually, yeah, that kind of makes sense. So if you then, I'll like just show a lot of the algebra steps. So if you were to then like multiply, so you can move this to the bottom, right? And then this becomes, if you like then move it into the square root, it's like r squared, omega squared, c squared plus, wow, this is such an extra way of doing this, but if you think about it, this is valid math here. So you get all this. And then remember, this question was asking, okay, this is for omega naught, right? So then if we plug in 1,000 for omega, right? Or actually, if we're leaving this in symbolic, okay, again, I'm doing all this, but I would highly recommend you just plug this into your calculator because this will get you an answer. However, we're doing this all in symbolic form. I'll just show the work. We had square root of 1 over LC for omega, right? So if we plug in square root of 1 over LC, all the omegas are squared though. So we get like R squared C squared over LC plus uh, LC over LC minus 1 squared. Wow. This all goes away, right? And then this, so this becomes like 1 over the square root of R squared C over L. And then this is the square root of L over R squared C. And then if you plug in all your values, you would get 0.1 over 20 times 10 times 10 to the negative 6, which gets you 5. And that would be your answer for the value of h of omega naught. Should we be required to show symbolic form on the quiz? If it asks you for a number, you can just plug it in and get the number. However, if you plug it in wrong and you don't show any work and you write down the wrong answer, then we cannot give you any partial credit. So I would highly recommend showing work, or at least show what you're trying to plug into your calculator. Because if you don't show any work and you get it wrong, then you will get fewer points than if you tried to do it symbolically and messed up some way along the way. So always recommend showing work. However, also highly recommend plugging it into your calculator and then doing the work and making sure your work lines up with what you get from your calculator. Yeah. Use your calculator to check your work. I guess if you don't have any time, you could just plug it into your calculator. But if again, if you get it wrong and you didn't show any work, you will get like 2 out of 10 on the question or something like that. So yeah. With that, I am out of time, so I will end the recording here.